Good evening. This is Miss Peterson. Welcome, AP Biology at the Center School. So today we're going to talk about water potential, and really that has to do with osmosis and plant cells. So water potential is the potential of energy to do work. So when we talk about potential, it's similar to gravitational potential energy. You might recall that if I have a big boulder on top of a hill, that it has potential energy stored in it because of where it is, and that potential energy is its ability to make something happen. Similarly, water potential is the ability of water to make something happen. So for example, plants use water potential in order to get water from the very tips of their roots all the way up to the tops of their leaves. So water potential, when we think about the potential of water to do work, or the energy potential that's in water, is based on two things. So it has to do with how many solutes are in that water, and it has to do with the physical pressure that's on that water. So those two things together are measured in water potential. And of course, because it's science and because it's biology, we have a fancy symbol that we use to represent water potential, and that is this trident, and we call it psi. So I always think of it as a trident like Poseidon, and that helps me remember both of those. So water potential is measured in megapascals. It's actually a unit of pressure, and 1 megapascal is equal to 10 atmospheres of pressure. So when we calculate water potential, we take water potential and it is equal to pressure potential plus solute potential. So let's think about these two things here. We have water potential, pressure potential, and solute potential. So solute potential is really the osmotic potential because solutes affect the direction of osmosis, or the direction of flow of water across a permeable membrane. So solute potential of any solution at atmospheric pressure is always negative, or that is to say it always affects water potential in a negative way. Why is that? Why would the presence of solutes make a water potential less? Well, that's because fewer free water molecules are available if there's a solute present in the water. So let's take ammonia as an example. Here I have some ammonia over here, and I have 4 water molecules over here. And if I dissolve that ammonia in the water, I will see that it hydrogen bonds to the water molecules, and those water molecules are not able to move or do work. So the other one is pressure potential. Pressure potential is the physical pressure on a solution. And pressure potential can either be negative or it can be positive. So for example, pressure can be negative, for example, in transpiration. If I have a tube or a pipe and something is pulling up on it and reducing the pressure that is there, then I would have negative pressure. Pressure can also be positive. So for example, if I have a cell or something that is enclosed, then the pressure inside of that would be positive. The standard for measuring water potential is pure water. So we start with that. And pure water at an open container at 1 atmosphere has a water potential of 0. So we say it has 0 megapascals of water potential. So let's look at how we think about this, and hopefully this will all make a little bit more sense to you. So right here, what I have is sort of a classic U-shaped tube, and down the middle I have a semi-permeable membrane that does not allow solutes to pass through it. And over on the right-hand side, we've added solutes, and over on the left-hand side, we have pure water. So if I look closely over here, the solute potential of this tube has been measured at negative 0.23 megapascals. It's in an open container, so the pressure potential is 0. If I add those two together, I would find a total water potential of negative 0.23 megapascals. Over on the left, I have an open tube, so it has no pressure, and it's pure water, so the water potential over here is 0. Water will always move from an area of high water potential to an area of low water potential. So if I think about it, which one of those numbers is higher? That's right, 0 is actually higher than negative 0.23, so I will find that water will move in that direction. And if I look closely, I will see that that is what has happened. So over here, the water is lower, and over here, it is higher. We can also remember that water flows from an area that is hypotonic, meaning it has fewer solutes, to an area that is hypertonic, meaning it has more solutes. So that is a tube with no pressure. Let's see what happens when you add pressure. So over on the right-hand side, now we've added positive pressure of 0.23 megapascals to the solutes that were already there, and we see that it has now evened out to 0 megapascals with the addition of this plunger. Over on the left-hand side, we still have pure water in an open container, so it has no water potential or a water potential of 0, and we see that it evens out and the water has not moved from left to right. What happens when we add actually just a little bit more pressure? So in this case now, we've added 0.3 megapascals of pressure potential. It still has a solute potential of negative 0.23 for a total water potential, remember we add them together, of 0.07 megapascals. Over on the left, we still have a tube that is open with pure water in it, so it has 0 megapascals. Remember that water moves from an area of high water potential to an area of low water potential, so it's actually going to move in this direction. And if we look closely, we see that the water is here on this side and the water is here on this side. That's an example with positive water pressure, or positive pressure potential. What happens when we have negative pressure potential? So similar to transpiration, this plunger is pulling up on the left-hand side on the pure water. So now I have solute potential of 0, but I also have a pressure potential that's negative of negative 0.30 megapascals. Over on the right-hand side, I still have a solute potential of negative 0.23, but the container's open, so there's no pressure there. So I have a total of water potential on the right-hand side of negative 0.23 and a water potential over on the left-hand side of negative 0.3. And this is honestly where I always get stuck and where the most mistakes are made. So if we look at those two numbers closely, which of those two numbers is less and which of those two numbers is more? Well, that's right, they're both negative, so that means that negative 0.23 is more than negative 0.3, and so water would move in this direction from left to right. So those are all examples of adding water potential in that tube, but what happens in cells? Well, let's take a look. This right here is what we call a flaccid cell. That means that it currently does not have any pressure inside of it, so the cell membrane is not being pushed up against the cell wall. The cell itself has a solute potential of negative 0.7, so the total water potential in that cell is negative 0.7. If I put it into distilled water in an open beaker, I would see that the water potential in that pure water is 0 megapascal. So which direction would the water move? That's right, it would move from the high water potential to the area of low water potential, or the area of hypotonic, fewer solutes, to the area of hypertonic, or more solutes. Therefore, the cell would become turgid, and the total water potential inside the cell will be at equilibrium with the water potential outside of the cell. Let's see what happens when we put a flaccid cell in a hypertonic solution. So in this case, we still have the same flaccid cell with a water potential of negative 0.7 megapascal, and this time we're putting it in a sucrose solution that is 0.4 molar. It is open, so there's no water potential, or a water potential of 0. The solute potential is negative 0.9, so the total water potential is negative 0.9 megapascals. Remember, water moves from an area of high water potential to an area of low water potential, so the water will move out of the cell. The cell will then go through something called plasmolysis, and it will plasmolyze. The cell membrane will pull away from the cell wall, and the cell itself will shrink. Remember that the cell will go into equilibrium with a solution outside of it, so it will stop plasmolyzing after those two are equal. So we know that water potential is equal to the pressure potential plus the solute potential. Okay, you will always be given this pressure potential, but sometimes you will have to calculate the solute potential. So the solute potential is based on the concentration of solutes and this equation, which is solute potential is equal to negative I CRT. This I right here is the number of particles that the solute makes up when it's mixed in water, and we'll talk about that in a second. C is the molar concentration, which is the number of moles per liter. R is the pressure constant, 0.0831. You might remember that from your gas laws in chemistry. You won't have to memorize it. That will always be given to you. And T is equal to the temperature in Kelvin. So let's talk about this I thing for just a second. So I is the number of parts that a molecule breaks up into when it is dissolved in water. So if I have a glucose solution right here, that means that I have glucose that is mixed into water. And when I mix it into water, then those water molecules will actually bind themselves to these hydroxide side groups over here and over here and over here, and they will surround the glucose and it will dissolve. But does the glucose break up into other pieces? It does not. It stays still one glucose molecule. In that case, I is equal to 1, or the ionization constant for glucose is 1. What about an ionic compound like sodium chloride? Well, if I were to dissolve sodium chloride into water, the water molecules will actually bind to each ion separately and separate them in the solution. So what I'll end up with is some sodium ions, and I'll end up with some chloride ions. That means that any ionic compound will break up into 2 or more pieces when I dissolve it into water. Really, all you have to do is identify something as an ionic compound or not an ionic compound. And how do you know if something is an ionic compound? Well, hopefully you remember that an ionic compound is a metal plus a non-metal. And if you can distinguish that, I'll write this here. So if you can distinguish that, you know that the ionization constant for an ionic compound is going to be 2, and an ionization constant for anything else like a sugar is going to be 1. And that's how you figure out I. So when we solve for water potential, if you know the solute potential, water potential is calculated by inserting values into the water potential equation. So water potential is equal to pressure potential plus solute potential. Remember that in an open container, the pressure potential is going to be 0 always. So you are going to have to calculate this in some cases. So here are some hints and reminders. So number 1, remember that water always moves from a high concentration of water to a low concentration of water. Remember too that water moves from an area of hypotonic solute concentration to hypertonic solute concentration. Remember that if you hear something about solute concentration, that's related to solute potential or osmotic pressure. Pressure is related to pressure potential. So if you hear about osmotic pressure, right, if the question that you're given or the word problem talks about osmotic pressure, that is solute potential. If you see something that is related to pressure potential, then that is the pressure. Number 4, pressure raises water potential usually. So most of the ones that you will be given have to do with pressure in a plant cell. Number 5, when working problems, use 0 for pressure potential in both animal cells and open beakers. There's only pressure present when a cell membrane of a plant cell is pressing against a cell wall. And then finally, 1 bar of pressure is equal to 1 atmosphere. Good luck, AP Bio. Stay curious.